Sir, we can start now.
Okay, sir. Is my screen visible to everyone?
Yes, sir.
Yes, sir.
Okay. So, good afternoon, everyone, and I welcome you all to this 1 week ATAL FDP program on intelligent computing in healthcare. And it's truly a good opportunity for me as well to interact with you on this prestigious platform given to me through NIT Raipur in coordination with the ATAL FDP. So as the theme for discussion in this FDP has been intelligent computing in healthcare. So the topic that I have chosen is non-linear filters for medical images. And we'll be talking about filter designing in this particular domain for medical images. And in true respect, we'll be discussing this entire thing in the purview of a research case study, which is very specific to breast cancer detection and diagnosis. So everything, every theory, every concepts that we'll be taking in, that will be surely in concurrence with some results, some published results, which have been done in this particular domain. So already my profile introduction has been given. This is my research areas where my primary area has been biomedical imaging, where different modalities I have used to work for early diagnosis of life-threatening diseases. Other allied areas where I have also worked are image filtering, denoising, signal fidelity assessment, image fusion, and biomedical signal conditioning. Now let's have an outline of today's session. In today's session, we'll be beginning with computer-aided analysis of mammograms, linear versus non-linear filters, mathematical modeling of non-linear filters. This thing we'll be taking in a crisp manner because certainly we have a short session, so we don't be given very much emphasis to the numerical
Sir,
or the...
sorry to interrupt you.
Yeah.
So please, slides are not moving.
They are not moving.
Yes, sir. Sir, slideshow कर लेंगे तो हो जाएगा.
It is not in slideshow.
Yes, sir. Slideshow.
It's already I have done it.
But from our side, sir, slides are only on the first one. So slideshows, I think, हो जाएगा. Now it's moving.
No, now the show has ended actually.
Okay.
Now it is coming. What
Yeah,
are
now
you?
it is. This is the outline of session. Computer-aided analysis of mammograms, linear versus non-linear filters.
Now it is visible, right?
Yeah, now it is visible.
Okay, fine. So coming to the outline of the today's session, I'll be talking about computer-aided analysis of mammograms, linear versus non-linear filters, mathematical modeling of non-linear filters. Here we will be skipping the derivative discussions or crude mathematical discussions owing to the paucity of time in this. Then non-linear filters, their existing challenges and research gaps with respect to this particular domain. Then non-linear polynomial filters, we will be discussing this as a research problem. And then we'll be focusing on what are the results which have been obtained from this research problem. And then finally, we'll be ending up with the directions for new research formulations in this particular domain. So generally, we have heard a lot about computer-aided diagnosis as a block diagram. Certainly, I'll be starting from there only. But just my focus to discuss in this is to narrow down on a small domain, that is filter designing. Because somewhat, sometimes it happens like that we as researchers, we tend to focus on taking up a very huge or very big application development. But at times, if we focus, then there is a lot of scope to research in a particular specific domain of interest as well. And that is this particular domain that I'll be taking up, that is non-linear filters for medical images. So when I certainly started working in this particular domain, say in 2011 or 12 something, then very less work was done in this particular area. And this was the first paper which I published, that was polynomial filtering framework for mammographic image enhancement. That was in IEEE Sensors Journal. And these were my two concurrent publications in this same domain. Even as a team, we have bagged a best paper award also, because this was a very novel area in that particular time. And in this span of time, we had a lot of other publications in this particular domain in very reputed journal. And finally, say in a research span of 10 years, recently I have published this book, say in early 2020, by the name Non-Linear Filters for Mammogram Enhancement. This book is concurring my entire research which I have done in this particular domain for early detection of breast cancer. It's a book available with Springer
Hello.
series.
Uh,
Hello.
Sir, sorry to interrupt you. Actually, the slides are not moving. Can you make it in an entire screen sharing mode?
Mhm.
I think only the window is shared.
I have made it sharing like a tab sharing is there. So how do you want me to share this?
Sir, I
Sir,
think you should stop presenting and you should again present it with your entire screen.
Acha, the entire screen.
Yes,
Okay,
yes.
just a moment. Now is my screen visible?
yes, sir. Sir, can you
Yes.
please move one or two slides so that we can confirm?
Okay.
Now it is okay, sir.
Can you see this graphic movement now?
Yes, sir.
Yes, sir. Yes, sir.
Shall I proceed?
Yes.
Okay. So this was the major content resource that we have published out of this research in this particular domain, say in last particular decade, by the name Non-Linear Filters for Mammogram Enhancement, published with Springer Studies in Computational Intelligence. So in this, the very first introductory topic that I'll be taking is computer-aided analysis of mammograms. So we have heard about the term CAD when we are talking about medical images or their analysis, and that is, say, by the name of computer-aided detection and computer-aided diagnosis. But there is one more term which is associated over here, which is named as computer-aided analysis. So let's quickly take up this fundamental to get it clarified, that how we are distinguishing in this particular three terms when we are talking about computer-aided diagnosis. So if you take a quick overview, this is the basic block diagram of computer-aided diagnosis system specific to when you are diagnosing some life-threatening diseases. So here, the initiating block is the medical images, which are our input. Then there is a need for pre-processing on these medical images, followed by there is feature extraction, feature selection, and then we have a classifier or a classifying stage where we are able to make the decision that whether the given image or the case is, say, a healthy image, or it's a non-healthy image, or it's consisting of or carrying some type of a anomaly. Now, the major challenge when we are discussing such CAD systems is not actually at the stage of feature extraction or at the stage of feature selection or classifier. The major challenge is generally when you are acquiring these medical images, because certainly acquisition part is not in our control. Definitely when we as researchers or engineers are working on it, we are just acquiring or using these pre-deposited databases which are being accumulated images produced by the medical hospitals or medical centers where they have accumulated these images for further researches. So the major problem that comes, or the major challenge that comes, is basically at the stage of when these medical images are acquired, and based on these challenges we are doing certain amount of pre-processing over there. Now, since the sensor system, the acquisition system for each of the medical imaging modalities are very, very different. So certainly it is very constrained to generalize a pre-processing thing if for all types of medical images. Say for a certain, if you are taking an example of an X-ray system, the acquisition hardware has its own challenges, has its own constraints. So definitely you need a different kind of a pre-processing filters over there. If you talk about MRI or say CT scan, they are little more sophisticated. So certainly you don't need to bank very strong pre-processing, or you don't need very strong pre-processing in such a particular cases. So if we talk about, say, particular case in this particular case study, our focus will be on the X-ray screening. That is, we'll be talking about the X-ray images. Now, X-ray images, if we talk about, then this is the kind of the X-ray images, and you can see the X-ray images of different parts of the human body. Maybe hands are there, legs are there, or elbow is there, or some spinal region is there, or the chest region is there. Now, certainly for breast cancer detection, the very initiating image, the very initiating modality for screening that is being used is the mammography or mammograms. And mammograms are nothing else, but they are the X-ray images of the breast. So we have to understand at this stage that how the X-ray of the breast region is little different from the other X-rays which are being generated. And certainly that is what that accounts for the complexity in analysis of these particular images in comparison to the other X-ray images. So you can see these are the just sample images of the breast mammograms. Now you can, if you see this particular zone where you have, say, X-rays of different other body parts, you can see that there is ample amount of sharpness in these particular images. You can very easily locate the things because of the good contrast over there. But if we see a mammogram or a breast X-ray image, you can see that these images are having very poor contrast is there. If you talk about sharpness, then the sharpness is also very low over here. And relatively, we can also say that if you talk about the signal to noise ratios, then certainly the signal to noise ratios also seem to be very, very low in these particular images. Now, these are also the X-ray images. The other samples which we have seen for other body parts, they are also the X-ray images. But why is this difference coming up in the acquisition is because of the amount of dosage that we are using for the acquisition. So if we just take a comparison, then you can see that these are the effective radiation doses that are being used for X-ray acquisition for different parts of our body. And if you see, then certainly the least amount of dose is being used with mammography. That means because of the sensitivity of that particular part of the body, very least amount of the radiation dose is permissible to acquire these particular images. And certainly, because of these health hazards, a very low dosage X-ray is being used. And what cost it certainly bears, or what compromise it certainly bears, is that the ultimate image is having very poor contrast. The signal to noise levels are also very low over there, and you can see that the sharpness is also not good in these particular images. So this makes actually these mammograms a very radiologically, you can say, difficult images to analyze. So if we talk about mammography, it is being an effective popular modality for screening of breast cancer. But as I already discussed, that because of the low dosage of the X-rays which are being used, and it's a relatively inexpensive breast examination, so it is a preferred mode for initial screening, for population screening, in comparison to the other sophisticated modalities like a breast MRI or a tomo scan, etc. But yet for the initial screening, this is a very, very reliable kind of a technique. Now, what are the challenges because of the X-ray acquisition performances? Then I have already told that because of these poor illumination and high noise levels over here, in your end images, the image contrast is affected, the signal to noise ratios are affected, spatial resolution is affected, and spatial resolution, we mean it is actually affecting the image sharpness. So from here, we can get a very good clue that when we talk about image enhancement on front end. So if you have a very general image for image enhancement, enhancement seems to be a very simple term over there, certainly a very simple filter over there. But if you talk about enhancement of these breast X-ray images or these mammograms, then actually enhancement should improve these three attributes that we are talking about. There has to be improvement in contrast of the image, signal to noise ratio of the image, and the sharpness of the image. So until and unless we have a enhancement filter or an enhancement algorithm which is taking up or balancing all these three attributes, we will later on see in the results that certainly that particular filter or that particular technique will not provide a sufficient amount of visualization. And that is why mammographies are among the most difficult radiological images. And therefore, certainly, you require a very senior, very experienced radiologist for analysis of these mammograms. So if you now take a more detailed insight into the computer-aided diagnosis, the very first modules are medical image acquisition and pre-filtering. So this is actually the pre-processing module. Now this acquisition part we are not doing. We are relying on the data sets. So just certain amount of pre-filtering is there. After this, we are coming to enhancement. Then there is a segmentation stage, because certainly when the medical image is properly visualized, the contrast is improved, the edges are improved, then certainly there is a scope for segmenting. You need to segment the region of interest. Suppose we have some tumorous region, which is you tend to see in that particular mammographic image. So you need to segment that particular region of interest for further analysis. So this is what we are calling as localization of suspicious region. And this particular module is known as the detection module, or what we term as computer aided detection. Now, just to differentiate this term from computer aided diagnosis, we certainly denote it by CAT-E. So this is what is known as the computer aided detection. Now, at this stage, you are just enhancing your image, you are segmenting your region of interest, and certainly the suspicious regions are marked or highlighted by the system. That is what we are getting at the end of computer aided detection. But certainly, if we want to employ a decision support system over there, so that in an automated manner, computer should provide you an assessment or evaluate that whether this particular suspicious regions are truly suspicious, are they totally, you can say, the affected areas, are they truly benign cancers or are they malignant cancer. So all that could be only possible if we go to the another module. So what we expect to do, we have to we ought to extract features from this particular region of interest, then certainly features, many features could be extracted. Now, if you talk about time optimization or to optimize in other aspects, we need not have to, rely on all the features. There could be numerous redundancy. So we do feature selection over there, feature optimization over there. And then at the last stage, we are doing classification just to classify that particular case or that particular image, that whether it is diseased or it is disease free, or it is a malignant cancer, or it is a, you can say, a non-malignant or a benign one. So this particular module is known as computer aided diagnosis module. So just to differentiate it with detection, we certainly refer it as CAD-X. So here now we see that when we say CAD of medical imaging, we generally have two terms over there. One is CAD-E and another is CAD-X. Now, the topic that we are taking up over here is a third term over here. Certainly that is computer aided analysis. So where actually we are augmenting this term computer aided analysis. Now, certainly we have to understand one thing, that when we are working, when we are practicing, when we are experimenting on these medical images, no doubt we as engineers are applying numerous computer vision image processing algorithms over there to visualize the image, to better the image, and to automate the results, to apply artificial intelligence over there, to and which could be, very accurate as 99% or 100%. But still, ultimately, the utility of that particular image is only to be adjudged by a medical expert or a doctor or a radiologist. So until and unless you have a fair assessment by a medical expert in that particular domain, you are not able to adjudge the trueness of this particular CAD module. So once you have an enhanced image, that means you have a proper visualization of suspicious regions in that particular image. Herein, a medical practitioner can intervene at this particular stage. He or she can analyze these images directly on the screen, right? With the help of our engineering tools, they can change the contrast, they can extract the region. All those tools are available for the helping part, for the support part. And with that, they can make a pre-assessment of these particular medical images. Now, certainly, this decision which is made by the medical expert at this particular domain can be further re-verified with the decision which is coming up from the computer. So definitely the computerized tool is behaving like a second opinion device over there, just to validate the decision made by a doctor or a medical expert. So certainly when we talk about this enhancement phase over here, then actually at this phase, we are talking about computer aided analysis. So in specific to medical images, one thing has to understood that generally when we are framing research problems in this domain, we are surfing literature in this particular domain. We see a lot of literature. We see people are changing different classifiers to get the results, to improve the accuracies. You are changing from machine learning tools to deep learning tools over there. Everything fine, everything done. But one point to be understood over there is that in the vein to apply these different advanced tools, we certainly tend to diverge from a basic fundamental that if your acquired image is poor in visualization, all the necessary diagnostic features are not properly visualized in that particular image. That means a very good or a very prominent enhancement algorithm or an enhancement filter is not applied over there. Then certainly, whatever advanced feature extraction algorithm you are going to apply, whatever advanced classifier you are going to apply, certainly the results on paper could seem to be say 99% accurate or 98% accurate, but in practice they are not going to give a satisfactory diagnosis if validated by a doctor or a medical aspect. So some way or the other, if we are working to research on these particular domains, there are a lot of scope if we particularly narrow down on the aspect of designing or developing algorithms in these particular domains. Because generally when we are referring to your MATLAB tools or Python tools, we are just relying on the inbuilt functions or libraries where we have, just very discrete kind of certain algorithms which are ready to use. No doubt, ordinary images, if they are there, those tools could be very good to just apply and see and improve the results. But if you are changing from one medical image to other, or if you are changing from one case to another cases in the medical images, then certainly your enhancement tool or your enhancement filter has to be really, really advanced in the manner to cater different cases of that particular medical imaging modality. So this is the insight of computer-aided diagnosis, detection, or what we understand as computer-aided analysis. So just a small demo I'll be showing over there, which will just give a pictorial demonstration on how the images for these mammographic images are processed through this computer-aided diagnosis system. Just a small visual example. Like when you talk about input images, the input images or the mammograms are somewhat like this. You can see that this is a mammogram. The pectoral margin is there, the outer periphery is there, and this is certainly the suspicious region, which is the tumor region. Say we have done some pre-processing, enhancement is done, and we see that this tumorous region has been extracted out as a particular region of interest. So till here, you are localizing your region of interest, your suspicious region. This is the kind of output that you get from a computer-aided detection system. Now, if you talk about the second module, that is your computer-aided diagnosis, then over here, if you have a detected region of interest, then say these are the different features which could be extracted, for example, from this particular detected region of interest. Now, definitely, when you are talking about a computer-aided detection system, the input is an image, the output is also an image. But when you talk about a computer-aided diagnosis system or a CADX system, your input is actually an image, but then it is processed in the form of the vectors or feature matrices. And then finally, you are getting analysis in the form of your numbers. So these are the extracted features. Now, maybe all the features could be redundant. So say we are extracting, or you can say we are selecting some of the features. Now, these selected features could be, you can say the selection can be done manually, or the selection can be done in an automated manner with the help of certain, say, feature selection or feature optimization algorithm. Now, once these features are selected, we are moving into form a feature vector, and they are then being given to a classifier where classification can be done that whether this particular region of interest is a malignant tumor or a benign tumor, then certainly this particular classification can be made. So this is how on screen an output occurs for a computer-aided analysis of mammograms. And when we say, then computer-aided analysis has a major step or a major module, which is known as the mammographic image enhancement. And when we talk about this mammographic image enhancement, over here, we have seen this particular enhancement tool work on three pillars. One is your contrast enhancement, another is your edge enhancement, and the third one is your improvement in signal to noise ratios over there. So whenever we are picturing out a computer-aided analysis approach for mammograms, at the back end, actually, you have to develop a mammographic image enhancement algorithm or a filter, and that filter should be accustomed to take care of these three aspects. And that is what that adds complexity, or you can say different challenges and specifically challenges are more when you are applying it on different types of cases. There are a lot of variety of cases when you're talking about analysis in terms of cancer diagnosis, and so makes the complexity or triviality of the particular enhancement approach. So early detection of breast cancer could be possible if you have a good computer aided analysis approach at your disposal. And once you have a early detection of this particular disease, certainly you can reduce the breast cancer mortality. Now, just to have a look on the type of mammograms. This is to be understood over there because there are numerous cases in study of such or diagnosis of such types of cancers, and at times each different category has a different way to handle through your medical imaging filter. So if you see the very first image over there, you are calling it a fatty mammogram. Then certainly fatty mammogram, you can see it's a grain kind of a image, and rather you can say a very clear kind of a image. So generally this kind of a mammogram is visualized in case generally when the age group of the patient is say above 50 years of age. Now coming to the next category, say category 2, that is scattered fibroglandular mammograms. Here most of the mammogram is almost clear. You can see just this cloud of tissues at some particular places. So certainly if I have a tumorous region over here, if I have a tumorous region over here, it could be very easy to detect those tumors, to visualize those tumors, to acquire the necessary diagnostic information from those tumors. But certainly if I have a small nodule or a tumor in this particular domain, so certainly this tumors are actually comprising of calcium deposits. So these are white. Now the background tissues over here are also white over here. So a white thing in a white background, now you can understand the how trivial it could be to locate the tumor in this particular region. But again, as this patch of cloud is really small, again it is very relatively easy to analyze such images. But if you come to this third category of image, now if I talk about this second category, then generally this type of mammograms are say in the age group of 40 to 50 years of particular age of the female candidate. Then third category is your heterogeneously dense breast images, and here you see that there is a dense cloud of background tissues, and again in this white background, if you have certain hidden tumors over there, locating this is a challenge, and certainly this is between the age group say 35 to 40 years of the age. Last is the most complicated case where you see extremely dense mammographic images. The density of the these tissues are very high, and generally in these cases tumors do develop over here, but generally because of this high density of tissues which are predominantly white, it becomes very difficult to locate tumors in such particular cases. So these are actually the category 4 are the very hard cases to analyze by the radiologist or doctors in terms of breast cancer diagnosis. And generally this is the age group which is say 25 to 35 years of age, and say the youngest age bracket. So certainly if you are able to detect a tumor at this particular age, then certainly a lot of treatment options are there, lot of things are there for further treatment, for medical treatment, or different other methodologies are there. But if a certain tumor is localized at this particular age group, then generally it is obviously converted to a malignant stage where it could be an advanced stage cancer, and certainly you are left with very limited treatment options in such a particular case. So generally category 1 and 2 you can see are the simple images relatively to analyze, but category 3 and 4 are the difficult images. So if you will be or anybody from you all have worked in this particular domain, or say tend to work in this particular domain. So when you will do literature survey, you will see that most of the images generally which have been taken for demonstration of results or the simulations or analysis, generally most of the examples which are taken are category 1 and category 2 images. But there are very few works which are catering to these difficult mammographic images for computer aided analysis and diagnosis. So I'll just suggest I'll be showing how results are being taken on this particular cases also. And it is just a suggestive that when you are taking up any of these, say, medical image diagnostic project to work, try to focus on the hard cases, the radiologically or medically hard cases of these, because if we tend to say work on say 8 to 10 or 15 say discrete these difficult cases, then trust me, this particular case study is itself going to be a complete work for an itself a very good publication in a very, very reputed journal. Because what is the trend in the past is that people are replicating same amount of databases, the same amount of images for their analysis just to prove the result better. But somehow, if you have collaborated with say some medical institute or some hospital or some doctor, where you get some say ongoing treatment cases, some live cases, and say if 5 odd cases are being analyzed by your filter, you have done you are applied AI algorithms, you are trying to give results, and those results are also validated by the medical experts, then certainly that case study is itself good enough a document for a good publication. So this was the categorization of mammograms on the basis of background tissues, and it is this diversity in the categorization of these mammograms makes this analysis very, very complicated, and detection of breast cancer is a challenge because of this. So this is the variation in tissue densities of the mammograms with age. So you can see that the density of the tissues are actually decreasing with increase in the age. When the patient is at the youngest age, you can see that there is extreme density of the tissues in those particular images. But as the age progresses out and you are coming at a later and a senior age, then at that particular time you have least density tissues, and certainly that makes the localization of anomalies very, very simple at that time. So coming now to the technical phase of the discussion, that is how we talk about non-linear filters or how we compare them with the linear filter. So if we talk about linear filters, then linear filters, spatial filtering, we all are aware of this fundamental concept. I mean, all those who have taken up the course of image processing, certainly they would be aware of the basic spatial filtering approach, where say this kernel is actually your filter kernel, filtering window. So you commonly name this approach as the windowing approach or the masking approach. And what we are doing, we are just overlapping your image, this mask with this particular filter. We are convolving this filter kernel with your input image, and certainly you are converging to a value which is being replaced in the targeted image. So this is a simple option, a simple way in which your spatial or your linear filters are operating. Now, if we talk about them, it is simply a convolution between your input image and your filtering operator. And this is how you are representing it mathematically. Say, if you have a single dimensional signal, and if I have a double dimensional signal like that of an image, so you are representing it in this particular manner. Now, linear filters are generally your low pass filters, and we have seen that these filters have been used in the past in noise filtering, contrast enhancement, edge detection. By changing these filtering masks, it has been used for all these different applications. But where the constraint comes is that with these linear filters, generally when your images are there with additive noise, or the noise on these images are, say you can say, are of pretty Gaussian in nature, these linear filters are very good to operate. But generally, if you have non-additive noises or non-Gaussian noises, then certainly these filters are not very good to operate, and there is significant amount of image blurring over there. So that is why this type of linear filters are not very suitable for processing medical images or certainly your mammographic images. So you can see the response of these particular medical images with the linear filters. You can see the filtering has been done, but significant amount of blurring, or you can say the loss of diagnostic details, is encountered when you are applying these linear filters on medical images. Now, when you are working on the concept of image enhancement, you cannot ignore one more concept, and that is known as HVS. When we say HVS, the full form means Human Vision System or Human Visual System. Now, your algorithm may be very good to carry out contrast enhancement. So if you have an initial image, you have a final image, and you see that the contrast parameter is very much improved or very much enhanced in your targeted image. But certainly, if your image is not visually coherent, it is not visually pleasing to the end user, certainly that enhancement algorithm is not very, very useful to us. So over here, I'll be just relating a very, very primitive concept. Generally, when we are studying image processing as a very, very fundamental lecture, we are generally taught about the concept of human vision and the, say, internal structure of the human eye. So there, we generally tend to relate one concept from there, that the response of eye to the changes in the intensity of illumination is known to be nonlinear. That means whatever image formation process from an object on the retina of our eye is actually following a non-linear pattern. So if we just go back and see, then the ratio of these intensities of the image formation on the retina is actually related by logarithmic factor. And log is certainly a non-linear component. So because the image formation process on the retina is following a logarithmic pattern, it's following a non-linear pattern, then certainly we draw the same clue when we are designing the display devices also. So similar concept of image formation where logarithmic of intensities ratio is being used and concerned, the same same concept is applied when you are talking about designing or image formation in the display devices. And this certainly gives us an impetus that why non-linear filters are much preferred for image processing. Specifically, if you talk about medical images, as our results are chances that it will be very, very coherent with that of the human vision system. So coming to the non-linear filters for enhancement are providing an improvement in the visual quality. Now, in what terms this improvement of visual quality is being provided? That you have reconstruction or visualization of diagnostic features. So with the linear filters, we have seen that there are loss of details, there are fading of details, there are blurring of details, but here you can see there is better visualization of diagnostic features. Another important attribute is to identify or evaluate the morphological changes. Now, when we talk about the morphological changes, it means the change in shape. So generally, when we are monitoring such medical images, we ought to focus that what are the changes in the diagnostic features. Suppose I'm taking the mammographic images or medical images, say after 1 month or at a span of 2 months or 3 months. So certainly I need to check over there that what are the change in the shape in the tumors or in the diagnostic features. So if my enhancement technique is somehow helping me to identify, to evaluate the changes in the morphology of the tumor, certainly I can very easily predict the growth rate of that tumor or I can predict the stage change of that tumor, that whether that tumor was initially in stage 1 and maybe now after 2 months it has come to stage 2. So this identification of change in morphology could be very much provided with the help of these non-linear filters. So you can see an example over here that, say, if this is a original mammogram, then certainly this is the enhancement with a linear filter. So you can see the linear filter is providing a similar kind of a image, not much change, but this is a tentative output from a enhancement with a non-linear filter. So you can see with a non-linear filter, certain amount of enhancement has been done. Although I'm not saying in any way that this response is a very, very good response. We'll be tending or converging toward how we get a good response, or what are the ideally good images in such types of medical images that we'll be seeing later. But this is a tentative output of enhancement with a non-linear filter. So coming to the next phase of discussion, that is mathematical modeling of these particular filters. So if I want to mathematically model these filters, then certainly for non-linear filters, the concept is being lifted out from a very traditional, very old mathematical series, that is your Taylor series. So this Taylor series, if you remember, remember your mathematics classes in your BTech or something, you can recall Taylor series. Or if you just recall your initial programming classes, then certainly this is a series for which you would have developed your C or C++ codes for generating such types of series in your C programming or C++ programming lab. So this kind of say series 1 plus x square upon 2 factorial plus x cube upon 3 factorial is a kind of Taylor series. And you see that over here different non-linear terms are coming up. So to mathematically model a non-linear system, certainly this non-linear series, Taylor series, was the first and very conventional experiment. But later on, this series, usage of this series for mathematical modeling was not very much extended or elaborated, because there were a lot of design complexity issues while using this mathematical modeling, and also there were very slow convergence with this particular series. So another series was taken by the name of, say, Volterra series, and this Volterra series expansion was certainly like this, that you have one DC component or a constant term over there, and then say sigma HLXN, where L over here is denoting, you can certainly, the order of your filter. So if we expand this particular series, then this series of this is of this particular nature. So if you see, this is your constant term from this series. This is actually giving you a linear term from this series, x and x. So you can make out that this is giving you a quadratic term, this is giving you a cubic term, and so on. So as this is, an indefinite series, so certainly the whole series cannot be used for designing of the filter systems. So what is the requirement? The requirement is to truncate this series at different points so that you can define different filters. So suppose if I do the truncation at this particular point, then I'll get nothing else, but I'll get a linear filter. If I do truncation over here, then say I'll get a quadratic filter. Over here, I'll get a cubic filter. Now we generally don't go or to more higher levels beyond the cubic system, because with the number of say higher powers, higher coefficients are there, then there are a lot of designing issues at such places. So generally we are not going beyond the order 3 with these particular filters. Now there are also options where you can combine this linear filter with, say, any of your higher order, that it's quadratic or your cubic components, to provide a bilinear kind of a system. So over here you can see that the truncation of this series will provide you different filter options, like a linear filter, quadratic, higher order cubic. Volterra filter is actually your bilinear filter, and then comes your polynomial filter. So it is polynomial filter is nothing else, but it is an improvement of your Volterra filter. And that is what is my contribution in this particular domain, where this particular filter has been utilized for designing filter or enhancement filter for these mammographic images. So if we take, say, the response of a quadratic filter, because certainly quadratic filter is, say, the very primitive nonlinear filter. So if you see this medical image over here, this mammographic image over here, then this is a suspected tumorous region. So say this is your input region of interest over here. So this is your input image, and you can see that this is your enhanced image that you are getting at the output of such a filter. So you can see that the brightness is increased, the contrast is improved, but also we notice one thing, that there is over whitening in this central region. So if you have over whitening in this central region, you are defining it as sometime overshoots. Sometimes you also call it oversaturation of intensities, you call it. And actually this oversaturation of intensities is nothing else, but it is caused due to the amplification of noise, because you are trying to improve the or enhance the contrast of that image, but in the verge of enhancing the contrast, the noise also gets enhanced. So it is not always that, you know, that noise should be appearing in the form of some pure disturbance. So it is also possible that noise could be appearing in any form which is giving you an unpleasant image. So over here, this contrast noise is appearing actually in terms of over whitening of these images. So it is this over enhancement, or you can say the over whitening of intensities, is actually because of the amplification of the unwanted noise, which is one of the drawback of this quadratic filter. Now cubic filter we are not using, certainly because of the rise in the number of coefficients and other designing constraints. So we have given away with the quadratic filter, we are given away with the cubic filter. So the next option that we are left out is certainly a bilinear filter or a Volterra filter. Now you can also see another example. This is enhancement with a linear filter, and this is how enhancement with a quadratic filter. So now coming to the Volterra filter. So as I told you that Volterra filter was a kind of a non-linear filter. It is a kind of a bilinear filter. So over here you see that this is your constant term, this is your linear component, and this is your quadratic component. So certainly this is a combination of your constant, linear, and quadratic, three components in one particular system. So you're calling it a bilinear filtering system. This is how the characteristic equation of this filter looks like. This is your linear and this is your quadratic component of this particular filter. So now, what does this linear and quadratic combination tries to provide you? Why we have taken it like this? So if you see, this linear component is actually operating like a low pass filter over here, because we have seen that linear components are good for noise filtering. They are good for providing noise smoothing effect. Now, if you talk about the quadratic filter, it is nothing else but it is acting as a high pass filter. It can provide contrast improvement and it can provide detail preservation. So what is the benefit of using Volterra filter is certainly that it is operating as a combination of linear and quadratic filter, or you can say it is operating as a combo of a low pass filter and a high pass filter. So I'm just skipping this mathematical part. Now, if we see the challenges which are associated with this Volterra filter response. So just see a very interesting thing. Suppose this is our input mammogram, input region of interest, and say we have done an enhancement. Now you are using Volterra filter for your enhancement. Now in the Volterra filter, you have a linear component, you have a quadratic component. Now certainly, if your quadratic component is dominating more, your linear component is not very dominating, then certainly you can see again the over enhancement, or you can say the noise amplification. So this is what is known as the contrast enhancement constraint. Now see another response. Now this is another example with Volterra filter. Maybe this time your quadratic component is not very dominating, but say your linear component is very dominating. So if your linear component is now very dominating, then certainly you can see it is doing blurring, it is diminishing the details, it is distorting the edges. So this is the kind of a response when your linear component is more dominating. So this is what is known as the edge enhancement constraint. So as we have seen that when we are doing mammogram enhancement, we have to focus upon contrast enhancement, we have to focus upon edge enhancement because the image has to be sharp. But finally, we see that there is a trade-off, because depending upon which particular component, filtering component is dominating, you are getting, say, an unexpected kind of a image. So when we say mammographic enhancement over here, we say enhancement of contrast, enhancement of edges, and there has to be a balanced noise smoothing also over there, because undue enhancement without noise smoothing could lead to over enhancement. And again, if you have sharpening but this noise smoothing is not controlled, then it can also cause loss of distaste. So this trade-off of edge enhancement and contrast enhancement is a really a big challenge when you are designing such filters. Then another thing, suppose you see this particular mammogram. Again, a quick visualization doesn't gives you a clear idea of this particular image. But if you see that there are some tiny white dots which are shown in these particular images. Now, these tiny white dots are called microcalcifications. They are actually the initial stages which are where, you know, the calcium accumulation process starts. And this is how these staggered dots of calcium get clustered, get accumulated, and then they result or form a ultimately tumor. So somehow, if you are identifying these microcalcifications, then it is very, you know, proclaimed to say that a suspected tumor is under formation. So again, when you are using Volterra filters, then if you see, again, there are over enhancement, and you can say the localization of calcification is not very smooth, because you see that most of calcifications which are certainly in this particular region, they are generally missed out because of the over brightening in that particular region or overshoot of intensities in that particular region. So this is another enhancement. This is another challenge with that of the response of the Volterra filter. So we have seen that with the Volterra filter, although it is a combination of a high pass and a low pass filter, but we see that there exists an extreme compromise between noise smoothing and contrast improvement, and another, there is a trade-off between noise smoothing and the sharpening, that is the edge enhancement. So what is expected is that you need to develop a mammogram enhancement algorithm where there is noise controlled contrast and edge enhancement, because ultimately if this noise part is not being controlled, either it will disturb the sharpness or it will disturb the contrast, because ultimately you are trying to achieve both through a single filter or a single algorithm. Then another challenges when you're designing such types of filters is that the variation of the image background. So we have already seen that you have different types of mammogram tissues with the ages, and with the background tissues, there are variation of images, and with the variation of images, generally you cannot apply the same type of filter, because maybe one type of filter which is very good on the fatty mammograms may not give you very good result on the dense mammograms. Another, there are certain mathematical challenge is also because determining the number of coefficients, the kernel size, and the optimization, they are also the challenges in designing your nonlinear filters. Now, if you talk about the expected outcomes of these non-linear filters, then there is one important concept which is to be understood over here, and that concept is known as the concept of simultaneous contrast. So if you see, if this particular block is in the foreground and you have three different backgrounds, so generally detecting this front block in this background is not good. But if you see the same foreground in this dark background, locating or visualizing this is very, very easy. So here you get a very good clue that when you are trying to do enhancement, what you are seeing, that due to little excessive enhancement, there is over whitening in the mammographic image, which is actually destroying the visual quality of your image. But if we don't stress much upon the enhancement, there is something which is known as suppression of the background, because the idea is you have to improve the contrast between the foreground and the background. So sometimes if you see that the mammogram is very bright, although there is ample whiteness in that particular image, then rather than, you know, increasing the contrast over there, you can start suppressing the background. So if you at time start suppressing the background over there, you tend to see a very good and sharp visualization of your anomaly, rather than just by increasing the contrast and increasing the noise in terms of the brightness. So if you see that with this background suppression, sometimes you get a very sharp lesion edges, that is the tumor edges, and you can also exercise very good control over noise enhancement and blurring. So I'm just replicating the past example. These were the image responses which you are getting with your linear filter and your, say, non-linear filters. But if you see this particular response, then this is actually the ideal, you can say the expected response of this type of filter. Because if this is the input image and if you're getting this kind of output image, I'll see how you're getting this image from the results of our filter, then you can see it's a very, very sharp image. The boundaries of this particular tumor are very, very clear. You can see these tentacles out here, which are all predictors of the morphology or the shape, and these are all conveying the diagnostic details to predict the stage or growth rate of that particular tumor. So this is the expected outcome for your nonlinear filters. Now coming to my contribution in this particular domain, that is your nonlinear polynomial filters. So nonlinear polynomial filters are being developed from Volterra filters only, because what we have seen is that in case of Volterra filters, what we have seen is only thing is that a compromise, a trade-off between the linear and the quadratic components has to be controlled. So how we have achieved this control is through these two parameters, gamma and lambda. So over here you see that this gamma parameter is being made as a tuning parameter in the linear part of the filter, and this lambda parameter is made as a tuning parameter in the quadratic part of the particular filter. So again, the filter is a combo of your high pass and low pass filter, or a linear and quadratic component. Again, only what we have done is we have incorporated two tuning parameters over there. One is gamma on the linear part of the filter, and another is lambda, which is on the quadratic part of the filter. Now, there are different ways, if we go into the mathematical details, how selection of the values for gamma and lambda are being done in different ways. That if it is coinciding with the central pixel, right, you are taking it A. If it is coinciding, if your mask is coinciding with the, say, the odd locations or at the even location, then you are taking this equal to B or C. So these are the different ways in which we are taking or developing the mask for this particular filter. And then with this, we see that if we segregate or open the response for this filter, then the response of this filter will be classified into three categories. Certainly that derivation we are not discussing over here, but the response of this entire filter will be into three. One is your type 0, another is your type 1, and third one is your type 2. So you have your three types of polynomial filters over here. So this is how your three polynomial filters are coming out from here. Now, experimentally, all these three filters were tried, tested on different types of mammograms, and there were certain types of analysis which were made. So what was concluded was that if you're talking about a type 0 filter, then certainly type 0 filter was providing very good noise smoothing, right? Now, if you talk about another category, that is type 2 filter, then type 2 filter was very good to perform sharpening of features and delineation of the lesion boundaries. Now, it was also seen that the response of type 0 filter was very good on the mammograms with fatty tissues. That is generally the mammograms which I showed in category 1 and 2. Now, type 2 filter responses were very good, say on the mammogram with the dense tissues, the one which I have showed in the category 3 and category 4. So what impetus that has been given or what has been derived over here is that a filtering framework has been designed over here, where you can say a linear combination of type 0 and type 2 polynomial filters has been taken. So this is being given name as a non-linear polynomial filtering framework for mammogram enhancement. And why we have combined type 0 and type 2, just with these two combination, you are trying to cover different category of mammograms, or you can certainly say all the category of mammograms through this particular combination of filter. So just a demo, I can show you that suppose we have images from the digital mammogram database, we are doing some pre-processing, and then we are applying type 0 and type 2 polynomial filters. We are superimposing their responses to get the enhanced image. So just a moment. So say these are our two images, input image, then this is the response of type 0 filter, type 2 filter, and this is how you're getting the response as the combination of these two filters. And so this is your ultimately region of interest, which is very similar to the one which I showed you previously. Okay, so you can see the similar response on another set of image. This is the response of type 0. This is the response of type 2 filter. And say this is the combination. So you can see over here that this region of interest has been enhanced. Another thing also which is to be focused, if you see this particular area over here, this may just appear like a normal area, but if you see this enhanced image, you can see a small developing tumor over there, and there are chances of few calcium dots to be located in the background also, which gives you a suspected idea that certainly there is some tumor also there. Along with this big tumor, there is a small tumor is also there into formation. Now, coming to the result part, so I'll be skipping much discussion on the image quality evaluation. So over here, we'll be talking about the image quality assessment measures for mammogram enhancement. So the most important parameter which is being used for assessing or evaluating the quality of mammogram enhancement is your contrast improvement index. So this is the formula that we are using over here. So this particular formula is actually evaluating the difference between the gray levels of the foreground region. So say this is your tumorous region, this is being considered as the foreground, and the immediate background is being considered as background. So we are taking the average gray levels of this foreground and the background regions, and their difference is providing the contrast, and you are doing it for the enhanced and the original image, and this ratio is giving you contrast improvement index. Now with this, we are also measuring two another parameters, that is PSNR and ASNR. Now just to give you an idea that although we are focusing upon say contrast enhancement, but why we are calculating PSNR and ASNR in combination with any of the contrast indices, it is always a trend, it is always mandatory, because we have to check that when you are trying to improve the contrast, no doubt you see a very good improvement in the value of the contrast. But certainly we have to check back that is that improvement is coupled with improvement of signal to noise ratio. So if that contrast improvement is also improving the signal to noise ratio of that image, then that means you can adjust that somewhere that the noise is not being enhanced during that process. But if you see that your CII value is improving, but your PSNR value is having a dip, or your ASNR value is having a dip, then certainly it gives you an example that say maybe the contrast is being enhanced, but because of the noise amplification, either there is over brightness, or you can see visually poor images obtained. So generally, when we are adjusting the quality of mammogram enhancement, we are taking up any contrast parameter, we always try to evaluate the signal to noise ratio over there in combination. So coming to the result part, how we'll be applying these nonlinear polynomial filters on the mammograms, and then we will be seeing the results and adjudging the quality with the help of CII, PSNR, and ASNR. So whatever images I have taken in this particular demonstrations, they are from two common databases, that is your Mammographic Image Analysis Society databases and Digital Database for Screening Mammography. These are two very old but very common benchmarking databases. Another one is a B-Screen databases, that is Bayesian Decision Support in Medical Screening. And as I have already told, that whenever one should go to work or research in this particular domain, no doubt you cannot avoid these two databases because they are now the benchmarking databases. So once you have to compare your performance of your results with anybody else's results, you have to take up images from these databases. But it is always advisable to collaborate with at least some hospital or some medical person who can, if you just provide you 8 to 10 different cases, live cases to work upon, then it is going to add a new dimension to your research work. So this is the link from at which you can just visit, and you can check out these links to download these different databases. So coming to the simulation setup, as I told you, that we are taking up, or you are finalizing a mask, a filtering mask, when you are applying these linear or quadratic or polynomial filters. So if you see that this is your input image over here, so this is your response of 3x3 mask over here. Then if you see, then this is the response from a 5x5 mask. And if you see the response of a 7x7 mask, there is significant amount of blurring in that particular response. So what we see over here, if we do a comparison by calculating the CII, PSNR, and ASNR values, we see that the results are very, very satisfactory with that of a 5x5 mask. So generally in our filters, rather than picking up 3x3 or 7x7 masks, we have taken up a 5x5 kernel for filtering. Moving next, this is another example. Say this is again the response with a 5x5 mask. And again, it shows that this 5x5 mask is giving you very good values in terms of CII, PSNR, and ASNR in comparison to those responses of 3x3 and 7x7 masks. Then these are the different values of the tuning parameters, the coefficients which have been taken for the analysis. Now, with these values which have been chosen for this filter, you can see that this is the original mammogram, and this is the, you can see the enhanced response that is seen. So this is your original region of interest, this is your enhanced, and then you can see the edges are very, very sharp in this particular image. Contrast is improved, and you can also see the significant amount of background suppression is also over there. Then this is the values of CII, PSNR, and ASNR. But yet, this is the response of the mammograms on fatty background, right? Certainly, I'll show you one example where you can see the mammogram results on the dense one. So you see, this is the example where the input mammogram is like this. It's a dense mammogram. So you can see this tumor region is camouflaged with the white tissues over here. But if you see the enhancement region, very clearly this tumor region is visible over here. And again, in terms of values of CII, PSNR, and ASNR, these are the values which we are getting. So generally, what we have proclaimed as the outcome of this particular research is that certainly with the change of our tuning parameters, there is a change in the look and feel of that particular image. Now, at times, good background suppression could be good to visualize the foreground, but there are cases where sometimes medical experts or radiologists also have to take information of the background of the image. At times, they are not very concerned with the foreground tumor, but they are also seeing that how that tumor is being spreading or interacting with the neighborhood background. So certainly, different change of parameters, you are getting different images. And these different images, you don't know that which image could be of use or how much of usage to the radiologist or the end user. So generally, what we have done is we have tried to provide a stable tuning range for generating these enhanced images, and certainly the end user has been provided that complete tuning flexibility that you can change the image from one parameter to other, and then the desired images could be choose from here. So if you see, say when we have changing the value of the parameter starting from say h is equal to 0.1, so this is the kind, this was the original image, this was the ROI, and this is the enhanced image that you are getting. These are the values of CII, PSNR, and ASNR. Now, the moment you are changing the parameter, you see your foreground is getting embossed, your background is getting suppressed, right? Now, till this stage, you can see you can have sufficient information of the background, but more and more as you are going back, you see your background is getting more and more suppressed. So again, the end user has to decide and pick up that which image or which set of images are useful for analysis. Maybe the end user, the doctor, has to take information from 2 to 3 images simultaneously, and then they can, figure out their diagnosis. But I have been calculating the value of CII, ASNR, and PSNR for our own reference, but certainly these values do not carry reference to the end user, because for them the ultimately image which is good for diagnosis matter. It hardly matters to them that what is the value of CII, ASNR, or PSNR. So this is how you are getting different images with the change of the parameters. So if you see this particular tabular comparison, you'll see the response of CII for type 0 filter, type 1 filter, and type 2 filter. And if you see the response of the proposed filter where type 0 and type 2 combination is used, then certainly all these CII values are very, very higher in comparison to each one of these filter responses. This is a set of comparative results in which different other techniques are used, and then for certainly the response of non-linear polynomial filter is being used, and you can see the distinguishing response and the difference or leap in the values of CII and PSNR is quite visible over here. You can see this another combination of results. So we have also taken the final opinion of radiologist in this case, and if you see that for different mammograms, these are the mean opinion scores which have been given for the original mammogram, and these are the mean opinion scores which have been given for the enhanced mammogram. So you can see that the subsequent change in quality has been noticed by the doctors or the end radiologists the way they have given this rating. So anyhow, if you are getting say 70% or 75% increment in mean opinion scores, then certainly that means a very satisfactory work has been, or you can say an above satisfactory work has been done by this particular mammographic enhancement filter. So as regards the directions for future result, future enhancement in this particular domain, one very good area where this work can be enhanced is that a lot of parameter determination is required with these filters. A lot of tuning parameters are there. So initial part you have to do a lot of manual tuning, but certainly if some amount of optimization is done in that domain, say you incorporate AI, say you merge it with some say genetic algorithm or say particle swarm optimization algorithm or any of the optimization techniques, then certainly on the basis of the nature of the image, the change in coefficients or the change in tuning parameters can be predicted, and the versatility or robustness of this particular filter can be treated. Another ways where this could be used for further research is that this particular filter can be combined or used with other approaches like unsharp masking approaches or multi-resolution approaches like your wavelets and contourlets. Another very good domain to work in this direction is that you generally have different image quality assessment metrics which are very, very generalized, and these generalized image quality assessment metrics at times are not giving you very satisfactory response in terms of the medical images or your mammographic images. So it is a die-hard need that some quality metrics should be developed which could be dedicatedly used for say particular imaging modality or say for categorically for assessing contrast change, signal to noise ratio change, or you can say the sharpness change in these particular images. So any budding researchers, if you are open up to take up challenges, then developing a quality metric is itself a good problem for research when you are taking up medical images. Then another thing I have already discussed with you, that working on dense mammograms is equally a challenge, as most of the researchers have been showing or demonstrating results on generally on the first two category of images. Then another thing is that, as I told you, that your edge enhancement or your sharpness detection should be very, very accurate, because you see that this is how there are changes in stages of the tumor from the very original benign state to the malignant state. So your filter should be able to accommodate, should be able to track these morphological changes in terms of edge enhancement or edge detection. So this is one area in which this filter or more research can be done in this particular domain. Then again, as I have told, that you have to assess that the response of this particular filter, the obtained response is just not giving you values in terms of say the quality metrics, but it's always giving you response in coherence to the human vision system. That is also important. So as I talk about the further research in this particular domain, say the initiating works which I have shown you that were in 2013 and 2015, then say in 2016, again, these polynomial filters were modified for edge enhancement, right? And this was published in Computer Methods in Programs in Biomedicine. Then recently, one of my scholar has applied genetic algorithm for optimization and tuning of parameters in these filters, and this work has been published recently in IEEE Sensors Journal in this recently May 2021. So don't think that this was a very big work. It was actually that that scholar has taken up a transformation function for enhancement, and he has just improved it by applying AI multi-objective optimization over there, just to improve the visualization of mammograms and showing the diversity of its this particular filter on different types of images. So I'm very thankful to these of my overseas collaborators who have somehow contributed with me in this particular research on mammograms. I'm also thankful for the medical advisory which I have received from time to time from these set of doctors which have been associated with me in this research. So recently, as a guest editor, I'm doing one particular special issue for a measurement in machine vision. So if anybody working in this particular domain where you're doing medical measurements and you are combining machine vision over there, then you can make your submissions in this particular domain. So another good journal where I am dealing as an editor is Recent Patents on Engineering. Again, it's a journal with Bentham Science and it's a Scopus Index journal. So anybody who are works ready, then they can submit their work in this particular domain. So I'll be just concluding my work with this thought that whatever is your definition of conceptual learning, you have to understand the basic concepts which have been taken up, and now you have to see that how well you can use this knowledge and then you can apply it to, make it in the form or present it in the form of some new research or new information. So with this, I put this session open for questions.
Okay, any questions from participants? One question which I can see is the data set publicly available?
Yes, the data set is publicly available, and I have also shared the link in that data set slide. So on that particular link, if you go, so all these different data sets are being provided over there. From there, you can go to that specific website and download that particular database.
So there is one other question. Rather than medical images, how can we continue with breast cancer detection?
Rather than medical images, I mean, say some way or the other, you have to take input in the form of the medical images only. Then only you can contribute towards breast cancer detection, because some way you have to apply AI, some way you have to apply image processing over there, and other domains could be, domains which could be not very good for, say, engineering, but they could be, say, the domains where somebody who's working in the pure mathematics domain, they can work on a very theoretical aspect whereby, developing differential models for tumor hypothesis and detection. But again, in that you cannot see any live results on the live cases that we are doing. You just will be working on a very, very simulative kind of an environment without any actual results in that domain. Yeah, definitely. I can see a question that can we continue on the data set of the repository? Yes, as I told you that if you are working on this particular domain, then definitely this particular data sets are must, which are to be used because they are the kind of benchmarking data sets now. Any other questions?
Sir, I think there are no further questions. So
Okay.
thank you very much, sir, for your informative
My pleasure, sir.
Yeah. So, sir, we'll be ending the session now,
Okay.
and we'll be reaching you soon. We'll be reaching you soon, sir. So,
Okay.
thank you very much
Yeah.
for giving
Sure.
your time.
Yeah.
So, I
Well.
think there will be lunch break now. Priyanka, can
Yes,
you
sir.
inform? Can you give further information?
Yes, sir.
Okay.
Participants, now right now there will be a lunch break. Next
Okay.
session will be from 3 p.m. from Dr. Rakesh Tripathi, NIT Raipur.
Okay.
So, thank you, sir.
Okay,
Thank you.
thank you, Vikrant, sir.
Thank
I
you,
hope
sir.
we meet soon.
Yeah. Yeah. Sure. Thank you, Mridu ma'am. Thank you, Bikesh sir.
Yes, sir. Okay, sir. Okay.